All right, last one for today, and you can see it's a multi-part question, so it's a bit of a doozy, and there's going to be a lot of notation here to follow, so I'll do my best to try and make it clear. But what's going to emerge from all of this is one of the really cool sort of, I guess, corollaries, things you can do with mod arg form that you didn't necessarily expect that you could do. We'll get to that at the end. You can sort of anticipate it just by the way the question is written, but we'll get to it in due time. So let's start from the top. It says, express this complex number in real imaginary form, so in Cartesian form. Now you can see you've got this complex number divided by this complex number. So another way of what they're saying is, can you realize the denominator and get this into a distinct A and a distinct B that you've got separated out rather than two complex numbers being divided one by the other. So let's have a go at that. This is part A. So it's got written as this, 1 plus I root 3 on 1 plus I. So to realize the denominator, I'm clearly going to have to multiply by the conjugate of the denominator. So that's 1 take away I on 1 take away I. What are we going to get? Well, on the top, I can start to expand this thing out. So you're going to get, if I distribute, let's distribute this guy to the 1 and also to the minus I, and then I'll do the same with the second term. You're clearly going to get 1 minus I, there's the first term, plus I root 3, this is me distributing the second set of terms, so there and there. This is going to be minus I squared root 3. I think I've got that right. You can double check my working. And then all of that is going to be multiplied by 1 plus I, 1 minus I, right? So this is going to be a classic, whoopsie daisy, A squared take away B squared situation here. Let's start to collect some like terms and tidy this thing up. So you can see here, let's highlight, these are going to be my real terms here. Even though this has i's in it, it's got two of them, I squared, so that's going to become plus 1 right in there, take away negative 1. So I'm going to get 1 plus root 3. That's just going to hang out the front. There's the first part of the real component. And then let's see here, if I factorize out that I there, so I'll do, whoopsie daisy, I might as well just stay in orange, that's fine. Factorize out the I, what's that going to leave me with? Well, you can see there's a negative 1 here and a plus root 3 here. So that's going to be negative 1 plus root 3. And therefore, on the denominator, I've got 1 squared plus 1 squared in the end, so that's just going to be 2. By the way, quick note before we go any further into this question, I just want to explain a bit, now that we've got sort of mod arg form and multiplication of complex numbers in that form a little more into our heads. Think about what's going on here, right? Why is it that we multiply by the conjugate to realize the denominator? Well, if you think about what a complex number and its conjugate look like visually, let's draw a really quick and dirty set of complex planes over here. 1 plus I, what is that? Well, it's going to be 1, 1, there it is. Let's call that 1 plus I. And then its conjugate, 1 minus I, will be here. 1 minus I. So here's one number and here's the other. Now what happens when you multiply these two numbers together? Well, two things happen whenever you multiply by a complex number. First one is your scaling, that comes from the real component, and the second thing is that you rotate, which comes from the imaginary component, right? Now, when they scale, this one is root 2, this one is root 2, and so that's why when you scale them together, you get 2, root 2 times root 2. But, and this is the really cool bit, right? What happens when you deal with the rotation? Well, because conjugates are in opposite directions, right? So here is the argument for this guy, and here's the argument for this guy. Because one of them is going to be, in this case, this is plus pi on 4, and this is minus pi on 4, the rotation of pi on 4 in one direction and the rotation of pi on 4 in the other direction, one clockwise and one anti-clockwise, they are going to cancel out. And so if you cancel out one rotation and that rotation, you end up just in the middle. Now, where is the middle? And the answer is the middle is on the real axis, right? So that's why this complex number multiplied by this complex number is the exact right rotation so that you end up back on the real axis. It's sort of like rotating one way and then rotating back, yeah? So that's why realizing the denominator has this effect. All right, let's finish by, well, I should say multiplying by the conjugate has this effect of realizing. I think a nice way to sort of tie this up in a bow is just to clarify what is the real component and what is the imaginary component. And you can see here this big fraction, this is 1 sort of plus root 3 divided by 2, and then it's separate to this guy being divided by 2. So I think we should write it like so, 1 plus root 3 on 2, there's your real component, plus, and then here comes the imaginary component, -1 plus root 3 on 2, and then that I is hanging out at the end. Whew. There's part A, there it is in real and imaginary form. Okay, in seemingly unrelated news, let's move into part B. Part B says, write each of these numbers separately. This is talking about the numerator and the denominator, and numerator, in mod arg form. They want us to convert into polar, and hence express this in mod arg form. Okay, so what I'm going to do for you is going to be, slightly long, but we're going to work it out together. We will be able to, in the future, prove some of the results that will make the working I'm about to show you a lot faster, but we haven't proven them yet, so let's just do it in long form, okay? Let's get each number in mod arg form. I've already started with 1 plus I. So 1 plus I, as you can see, even from this quick dirty diagram over here, it's going to have a modulus of root 2, and then its argument is going to be, as I was discussing before, pi on 4, right? So therefore I can say this is going to be cos pi on 4 plus I sine pi on 4. Okay, so that wasn't too hard. What about the other one? Well, 1 plus I root 3, think about this, right? This is going to exist in another right-angled triangle, like so, where you've got, this is the real component, this is the imaginary component. So I need to know this length, the hypotenuse, to work out the modulus, and then I need to know this angle here to work out the argument. And hopefully both your Pythagoras and Trig are good enough that you will be able to recognize my modulus here is going to be 2, and then my argument here is going to be pi on 3. Okay, so there are the two numbers. So then how do I express this division here in mod arg form? I want it as one single number. Well, it's going to be this guy divided by this guy, which means this is the numerator, this is the denominator. So what does that end up with? Well, I'm going to say this equals, in fact, I'm just going to be slightly lazy. I'm going to duplicate this guy and going to duplicate this guy. And I'm just dividing one by the other, like so. Okay, so this is let's see here, 1 plus I root 3 divided by 1 plus I, but it's not in mod arg form yet. I've got the two complex numbers sort of separate, so how do I combine them? Well, this is going to require some knowledge of trig here, and it's going to get messier before it gets neater, so stay with me, okay? Let's do the easy part first. 2 divided by root 2, those moduli are easy to deal with. 2 of course is root 2 times root 2, so a root 2 will cancel, which gives you just root 2 on the top. That's nice. What do I get when I am trying to deal with this guy and combine them into one? Well, even though it's going to look in the short term very, very messy, and I'm actually going to go down here, I'm going to need the whole length of the line. I'm going to basically do what I did before, right? Which is you've got to multiply by conjugates in order to realize the denominator. It's just that my conjugates are going to look somewhat messier now because mod arg form tends to be much longer to write. So let's go and get stuck into it, right? What I'm going to do is I'm going to multiply by the conjugate of this denominator here. So instead of cos pi on 4 plus I sine pi on 4, I'm going to multiply by cos pi on 4 minus I sine pi on 4. So let's have a go at that. You can see this part is going to stay the same, so I'll just duplicate this down. But let's multiply through, and this is what you're getting normally, and now the conjugate looks like, whoops, I'm using the wrong tool. Know what you're doing, there we go. That's going to be, if I can keep the right bits, that's going to be the conjugate right there. There's the minus instead of the plus, so we'll duplicate that. All right, now you're looking at this and you're thinking, oh my gosh, this is gonna look gross. It is gonna look gross for the time being, but stick with it because a beautifully elegant result emerges. Let's start it out. To begin with, and I'm just going to begin expanding things because there's no sense, there's no reason to put it off, right? I've got this root 2 hanging out the front, and then what happens when I multiply this mess together? Well, let's have a go at just distributing terms through, right? So I'm going to have cos pi on 3, and it's going to multiply by each of these terms here and here, right? So I'm going to get cos pi on 3, cos pi on 4. And then I'm going to get minus, we'll put that I out the front, and I still have cos pi on 3 that's being distributed. This time it's 2 sine pi on 4. So far so good. So what I've done is I've multiplied this first by cos pi on 4 and then second by I sine pi on 4. So that's what I've got here. All right, next term to distribute, it's going to be this I sine pi on 3. So I go I sine pi on 3. First I multiply by cos pi on 4 like I did earlier. And then watch out because you've got a minus and another factor of I here. So it'll be minus I squared sine pi on 3 sine pi on 4. My goodness, that looks disgusting, but that's okay. It's going to come good in a second. Before we return to this numerator, let's deal with the denominator. So what I've got here, like I always do with trying to rationalize or realize denominators, I'm getting difference of squares here between here and here, right? So clearly the point of this was to get an a squared minus b squared situation on the denominator, which in this context is cos squared pi on 4, there's my a squared, and then minus, here comes b squared, it's I squared sine squared pi on 4. Okay, so it's I sine pi on 4, which you got from here, the whole thing's been squared, so there's the I squared, there's the sine squared, I'm good to go. Alright, now, I've been putting off dealing with this numerator, it's time to address it. As I've done before, I'm going to use colors to help clarify what's happening here. And you can see, as always with a complex number, there's the real parts and then there's the imaginary parts, and I want to deal with them quite separately. So here is the first real component I see, there are no i's. This part on the end here is also going to be real because that I squared is going to factorize out to be just -1, right? In the same way, you're going to have this guy in here that has an I in it, clearly, so it's imaginary. And same deal here, that's got an I term, so I'm going to have to deal with that. So let's deal with them and sort of put them beside each other and separate out. I've got this, oopsie daisy, I've got this root 2 hanging out the front, and then let's write all the real components first. So I've got cos pi on 3, cos pi on 4. And then I've got, be careful, this is the minus times -1, so that's what I get with a plus sine of pi on 3, sine of pi on 4. Take a breath, that's all the real components. Now we do the imaginary components. So I'm going to have plus I, and I notice, you know, this one's negative and this one's positive, so I'm going to write this one first, just for convenience. I've already factorized out the I, so that leaves me with sine pi on 3 cos pi on 4. Minus cos pi on 3 sine pi on 4. So you can see I'm writing this in terms of the angles. So pi on 3 always comes first, pi on 4 always comes second. All right, what am I going to get down on the denominator? Well, we really need our exact values to be on hand very quickly. So cos of pi on 4 is 1 on root 2. So we're squaring that, cos squared. So 1 on root 2 times 1 on root 2. Last I checked, that was a half. Here you're getting minus I squared, we saw that up above here, so that just becomes plus. And then nicely for us, sine pi on 4 is also 1 on root 2. So 1 on root 2 times 1 on root 2 is a half, so I'm adding a half. How convenient, this whole denominator here is just going to be 1. So from this line on, I don't need to worry about it. Okay, now this still looks like a mess. What can I deal with this, right? How can I deal with this, I should say? Well, if you have a look at this term here, or this pair of terms I should say, even though it looks so awful, I wonder if it rings any bells from your trigonometry earlier this year. I forgive you if it didn't because it's been a while, but hopefully it's sort of like ringing your head like this cos, sine, sine, where do I recognize this from? And if you need a bit of a memory prompt, if you go back to your reference sheet, if you go all the way to page 2 under trigonometry, you might see this compound angle business going on down here, right? So you can see cos of a plus b looks a whole lot like what I've got here. Do you see that? It's that same cos, sine, sine, but over here, instead of having cos plus sine, sine, I've got cos minus sine, sine. So what you can see on the reference sheet there, what's being quoted for you is the sum of angles, the sum of, you know, a plus b. But here I don't have, you know, the minus sign that's in the reference sheet. I've got a plus. So it's actually the opposite case. This is not cos a plus b. This is cos a minus b. So what I can write is, let's stay with the same color. The cos of a minus b I'm going to get in this context is pi on 3 minus pi on 4. And then I've got a plus. And now that you've seen the connection with the compound angle for cos, you might also recognize that this tangled mess here is going to give you the compound angle for sine. It's the same deal though, right? See how sine A plus B, it's got a plus sign in between, sine A cos B plus cos A sine B. Well, the fact that I've got a minus sign here means it's my opposite. It's not sine A plus B, it's sine A minus B, which is a relief because I can get rid of this now. in mod arg form, I'm supposed to have the same thing, the same theta on the cos theta plus I sine theta. Those angles are meant to be the same. So it's a relief for me that I'm getting pi on 3 minus pi on 4 in the front and in the back as well. And so at last, whew, we finally got there. I can actually simplify this out and write it in mod arg form. Now that I have everything in my, here comes my r, this is my cos theta plus I sine theta. Now, maybe you don't know your a third minus a quarter off the top of your head, but the question itself gives you a clue because you can see where they're headed is pi on 12. And of course, pi on 3 is 4 pi on 12, and pi on 4 is 3 pi on 12. So when you subtract them, you're getting 1 pi on 12 minus I sine pi on 12. That was a lot. That was a lot of trigonometry. This result in here, by the way, that took us all of this expansion, all this kind of thing. Basically, these three awful looking lines in here, we are going to take that as a proven result a little bit later in the course. That's part of why we use mod arg form. We don't have to go through all of this every single time. We can just show there is a subtraction of angles and a division of these moduli here. Now, how can I conclude this? How does this get me cos pi on 12 in surd form? This is really interesting, right? Because cos pi on 12 is not something that we have in exact values. At least it's not something we ask you to memorize. We ask you to memorize like 0, pi on 6, pi on 3, pi on 4, I skipped that one, pi on 2, and multiples thereof. But pi on 12 is not one of them. However, we can see that it's in here, right? So how do I get this in terms of surds? Well, thankfully, I want to remember, like, where did I get this from? This whole complex number to begin with. Well, where I got it from was from this division, right? This division was, in fact, 1 plus I root 3 on 1 plus I. So I can actually say, based on part A, which I seem like I did a lifetime ago, right? Here is the same thing. This is 1 plus I root 3 divided by 1 plus I. And down the bottom, what I just got out of my mod arg form is also 1 plus I root 3 on 1 plus I. They're the same thing, right? So in other words, I'm taking this one object and I'm looking at it from two different angles. So I can therefore say this is part C. Part C, this guy here, I first did it in rectangular form. It's identical to this. I just did it in mod arg form. So we're going to pull out a trick that we did from last week, which is to compare the parts on the left and the right hand side that are useful to me, which in this case is going to be, I think this is the color I used. This is the real component on the right hand side, and this is the real component on the left. So I say compare real parts. That gives me, I'll put the cos pi on 12 on the left hand side because that's where I want it. Root t cos of pi on 12 equals 1 plus root 3 on 2. So now just to get cos pi on 12 by itself, cos pi on 12, I'm just going to divide both sides by root 2. So that gives me this. And now you can see why we don't make you memorize the exact value for an angle like cos pi on 12, because gross 1 plus root 3 on 2 root 2, I don't want to have to commit that to memory. But isn't it amazing that actually going into complex numbers, which sounded like it was very exotic and weird and strange, actually gives us insight to parts of mathematics, namely trigonometry, that we've been dealing with for years, but we couldn't answer before. If you take cos pi on 12, put it into your calculator, it's going to give you some weird garbled number. In fact, it's not going to give you just any weird garbled number. It's going to give you, there's a previous calculation I was doing. Let's see, it's going to give me cos of pi on 12. There it is, 0.9659, etc. And I can confirm that I got the right surd by putting in 1 plus root 3, and then I'm going to put 2 root 2 on the bottom, and that looks pretty good to me.